Hi, this is Dr. N.K. Ilango, Professor, Department of Electrical and Electronics Engineering, K.S.Rangasamy College of Technology. From this video lecture, I would like to explain the concept modeling of power system components. Let me explain what are the content I am going to explain in this today's video lecture. The first one, introduction on modeling, modeling of generator, modeling of synchronous motor, that is power system components. We know that generator, synchronous motor, transformer, transmission line, induction motor, right? I will explain the modeling of those things. What is modeling? Actually, the power system component modeling uses mathematical representations to simulate generators, transformers, transmission lines and loads. Actually, it's essential for power flow analysis and stability studies. See, we know that what is modeling? That is nothing but mathematical representation of any quantity. It may be an electrical quantity or it may be a mechanical quantity. So in order to do some simulation in computers before getting into the product, we should have the mathematical representations of any process, that is called as modeling. So for that power system network, we are getting modeling of all the components of power systems. The first one, modeling of generator. See that modeling of generator, that is the equivalent circuit of generators. See, the first diagram shows that three-phase synchronous generator equivalent circuit, and the second one diagram shows that single phase synchronous generator equivalent circuit, right? See, we know the three-phase synchronous generator, it has three number of windings called as R phase, Y phase and V phase. Each winding has the inductive reactance and the resistances, right? So the inductive reactances represented as Jx and the resistance is nothing but R, right? Simply we call it as synchronous resistance and reactances, and it may be connected in star connected systems or delta connected systems. And in per unit concept, I explained to you that it will be converted into a single line diagram. So the three phase synchronous generator represented into the single phase synchronous generator equivalent circuit that shows in the second diagram. It gives that voltage EA, that is nothing but a generated voltage by the synchronous generator, and it has the components, impedance, synchronous impedance called as ZS, normally the combination of synchronous resistance and synchronous reactances. Normally the synchronous resistances are going to be neglected for their lesser value compared with that of synchronous reactances. So the modeling of generator, synchronous generator, it is simplified as like this. Here the current IA will be coming out from the generator, and load voltage is nothing but a V suffix load, or we can call it as V phase load, that will be given into any motor, or in power system network that will be given into transformers. So the modeling of generator is nothing but a equivalent circuit of a synchronous generator that has the components EA, JX and RS. RS is neglected. And modeling of synchronous motor, this same with that of previous one. It is also has the two components, that is armature reactances, synchronous reactances. For simplicity, we are neglecting the armature resistances, so it will be call it as a synchronous reactances only. So only the difference in between synchronous motor and the synchronous generator, the current direction, current coming out from the generator is known as generator. The coming will be coming into the machine is called as motor. That is the difference in between synchronous motor modeling or synchronous generator modeling. Then the circuit diagram shows that modeling of the transformers. See, we know the transformer consists of two windings. One is primary winding and another one is secondary winding. Primary winding is also has the impedance components, just like synchronous generator or synchronous motor. Resistive component is there and inductive component is there. So in primary, R1 X1, and in secondary, R2 X2 will be there. In addition, magnetizing component is also be there in the transformer. That is, magnetizing current is also going to flow through the winding. By the operating principle, you understand the concept of magnetizing current and magnetizing component, that is IW and I mu. Here the diagram shows that equivalent circuit of a transformer. There is nothing but a modeling of a transformer. See here, the first diagram shows that V1 is the primary voltage applied to the transformer, and the magnetizing component will come into the picture. The current flowing through the component is I0, and the remaining part current will be flowing through primary and secondary. Here the secondary winding will be transferred into primary winding. Secondary winding will be transferred into primary winding. That will be represented into suitable equation with the help of transformation ratio. So the modeling of transformers has the following components: R0, X0, R01 and X01, where R01 is the equivalent resistance referred to primary, that consists of primary resistance, and secondary resistance referred to primary, and X01 is also the reactances of the transformer referred to primary, that consists of primary winding reactances, and the secondary winding reactance referred to primary winding, that will be converted with the help of suitable transformation equations. Then transmission line. Normally the medium transmission line represented into two types. One is T type and another one is pi type. Again the components of a transmission line: resistive component is there, inductive components, and in between two conductors capacitive component is also be there. For T type representation, resistances will be half before the capacitance and after the capacitance, which is sending end side and receiving end side. So it will be represented as R by 2, L by 2, and for receiving end side, again the resistive and inductive components will be half of R by 2 and L by 2, and we know that current IS will be flowing from the sending end, and receiving end current will be flowing to the receiving end side. This is the T type representation of transmission line modeling. And for pi type, here the resistance and inductive components will be represented as the whole amount, but for capacitances will be half between two, R and L, C by 2 and C by 2. So here current IS is the sending end current and IR is the receiving end current, and similarly IC1 and IC2 are the capacitances which is flowing through the capacitive current which is flowing through the pi type network. And modeling of induction motor, this is also just similar to that of transformers modeling, only the difference load how we are going to represent it, right? The mechanical load applied to the induction motor represented as RR dash, that is equal to 1 by S minus 1 times of RR, that will be resistance representing the load, that is also referred to primary side, right? And R and X is X, these two are just similar to that of transformers. So this is the modeling of a induction motor. Thank you.